Okay, hello everybody to this week's ISGC seminar talk. Today's speaker is Hayato Motohashi. He received his PhD from the University of Tokyo in 2013, and since 2025 he is an associate professor at Tokyo Metropolitan University. Thank you very much for agreeing to give this talk. The stage is yours.
Okay, thank you very much. So I'd like to first thank organizer for inviting me to this nice seminar series. And today I would like to talk about this non-Hermitian perspective of gravitational physics, especially focusing on the black hole perturbation theory. And this talk is based on my recent work, and there have been also several articles written for a broader audience. So if you are interested in non-technical introduction of this topic, so those may be helpful. And in this talk, I will focus on underlying physics. Okay, so I will first give a brief review of these black holes and gravitational waves, and then I will explain the quasinormal modes, especially from the non-Hermitian point of view. And then I will discuss this avoid the crossings and resonant excitation phenomenon, and then further recent progress in this field. And I will summarize my talk. Okay, let me begin. So this is a frontiers in gravity. So why black hole is interesting? Because it's related to frontier in gravity. So as is well known, so this inverse square law or generativity has been verified very accurately from the sub-millimeter scale to 10 to the 8 kilometer scales. However, gravity remains poorly understood yet beyond these regimes. So namely, these long distances or short distances, and also dynamical regime or strong field regime. And the cosmology mainly address these long distances and short distances scales. And black holes is studying these short and dynamical and strong field regimes. And quantum gravity may be related to all of them. But today's topic is this black holes. Okay, so black holes now has a very long history. And Schwarzschild first found a non-rotating black solution right after the proposition of the Einstein generativity. And after that, Roy Kerr found a rotating black solution, and Penrose proved that these are not only the theoretical solution of the Einstein equation, but also the astrophysical objects collapsed into the black hole in real universe. Since then, there have been many observations now, starting from observation of jet, and motion of stars at the vicinity of the black holes, and gravitational waves, and shadows of the black holes. And I will focus today on these gravitational waves emitted from black holes. So black holes are very interesting objects because they have strongest gravity, and also they are actually simplest objects in the universe, in a sense that in generativity, stationary and axisymmetric spacetime is just a only Kerr spacetime. This is a unique solution. So, and the Kerr spacetime is characterized solely by mass and angular momentum. So this mass is m, and a is a spin parameter related to the angular momentum of the black hole. So this is very important, and we can now remind that this hydrogen atom, role of a hydrogen atom in the early days of the quantum mechanics. So because this study of the hydrogen atom, which is the simplest quantum bound state in quantum mechanics, was very important to develop the foundation of the quantum mechanics. So in that sense, so these black holes are some gravitational hydrogen atom and should be very important to obtain a deeper understanding of gravity. And these simplest features are very important because we can check so after observing many gravitational waves from many black holes, So we can check that whether these gravitational waves from black holes are described by only 2 parameters or not. And then it is directly related to the test of the general relativity. So this strategy is known as black hole spectroscopy program. It's a robust test of GR. And this is our latest review about this point. Okay. And then gravitational waves. Now it's 10 years from first detection in 2015 and Nobel Prize. And now we have already almost 300 events detected by a global network of the gravitational wave interferometers. And this is a future plan, observational plan of the LIGO-Virgo-Kagura collaborations. So more and more gravitational waves should be observed in the near future. And gravitational waves shares some common features with electromagnetic waves. They are transverse waves propagate with light speed and 2 polarizations and energy transportation. But the difference is the gravitational waves caused by the accelerating motion of mass instead of electric charge. And due to the absence of negative mass, it starts from quadrupole. And it's very, very weak compared to these electromagnetic interactions. So weakness of these gravitational waves is a main reason why we took 100 years after the Einstein's prediction of gravitational waves. But once detected, then these gravitational waves can be used as a very clean a source of information of for example, this at the space-time at the vicinity of black holes. So this is a simulation of the gravitational waves emitted by the binary black hole merger. And you can see that these gravitational waves has some peak when they merge and then quickly decay right after the merger. And that's the main regime we are interested in this talk. Okay. And such a regime is called ring down and described by quasinormal mode. Okay, then I will explain this. So this is a schematic picture of the merger of the binary black holes. So first phase is called in spiral. So this is the almost Kepler motion, and we need to take into account some correction to Kepler motion. Then this is merger, very highly non-trivial nonlinear phase. And then after that, black holes are ringing down to the stationary single black holes. So each phase can be analyzed by a different strategy. So first, this in spiral phase can be studied by using post-Newtonian expansion. And merger phase, this is can be accessed mainly only by numerical relativity. And ring down phase, we can study this regime by using perturbation theory about stationary black holes. And this is the schematic picture of the gravitational waves. So this is positive in spiral phase. There's a merger phase and ring down phase. Okay, so this is a main topic of this talk. So this ring down phase. So let's zoom in this part. And this is absolute value in the logarithmic scale. Then a black hole perturbation theory tells us that these ring-down gravitational waves can be mainly described by the superposition of the so-called quasinormal mode frequencies, quasinormal modes, damped oscillations. So this is quasinormal mode frequency, omega. And this is some amplitude, QNM amplitude. And both are complex quantities. And yes, QNM frequencies, the real part corresponds to the real frequency, standard frequency, and imaginary part corresponds to the decay rate. And this is infinite number of quasinormal modes. And we label them from 0, 1, 2, 3, 4 by using the ordering of the lifetime. So this n equals 0 is called fundamental mode, which has a longest lifetime. And this is n equal 1 is the next longest lived one. This is called first overtones. The second one is the second overtones, and third one, fourth one, and so on. So such a structure arises from the analysis of the linearized Einstein equations, so known as Reggie-Wheeler-Zeleri equation for non-rotating case, and Chukovsky equation or Sasaki-Nakamura equation for rotating case. Here, this R star is torus coordinate. Infinity corresponds to the spatial infinity, and minus infinity corresponds to the event horizon. So we are interested in the range from minus infinity to infinity in terms of torus coordinate R star. And omega is a frequency, and this is V is an effective potential, and psi is gravitational wave strain, master variables. Okay, but this is mathematical sense. This is just an ordinary differential equation, second order differential equation. Yes, after Laplace transformation, actually this is based on the wave equation in curved space-time. So this is related to second time derivative, but after Laplace transformation, we in the frequency domain, we obtain this kind of equations. Yeah, Chukovsky has a more complicated form, but basically essentially the same. Even we can recast this equation in this standard form. Okay, so let's mainly focus on this standard form. And this form is very similar to the Schrödinger equation in quantum mechanics. So this is second derivative and the energy eigenvalues and the potential and the wave function. So of course, this is wave function and we have probability interpretations, but this is a classical field, just a classical field, not a wave equation, a wave function. However, the form of the equation is very completely the same. So we can make use of this analogy between gravity and quantum mechanics at the level of equations, differential equations, which is actually emphasized in the Feynman lecture series. So this is one section from volume 2. The section title is same equations have same solutions, of course. But the point is that the equations for many different physical situations have exactly the same appearance. So if we have some knowledge for one subject, so one side, for example, for quantum mechanics, if one knows quantum mechanics in detail, then we can immediately have a great deal of direct and precise knowledge about the solutions of equations of another. So that's very interesting point and powerful strategy in physics. And actually, the history of the development of the black hole physics follow this rule. So we, from gravitational side, we import this WKB technique and continued fraction technique, originally known as Jaffe series in quantum mechanics, but now in gravitational physics researches, we know that it's called Rieber's method and scattering theory too. And we see that there is a roughly half-century gap between this quantum mechanical side and gravity side. But my point is that these are mainly related to the bound state in quantum mechanics, but I would say that more direct correspondence to this quasinormal frequency, quasinormal modes in black hole physics should be this non-Hermitian physics. So non-Hermitian physics was pioneered by Gamow. So this 1928 paper, so his paper in German, and he set a E to be complex. This is a complex eigenenergy, and the real part corresponds to usual energy, and the imaginary part is decay constant. So in this way, Gamow developed his theory of alpha decay, and has been utilized in the nuclear physics and particle physics. And later, it's generally used in open systems or dissipative systems. And more recently, there are much progress in the condensed matter or solid state physics field. And there are many nice textbooks and review papers about this topic. So from that point of view, this quasinormal mode physics is very related to this, for example, alpha decay theory, gamma theory. Okay, in the quantum mechanics side, for alpha decay, we consider this kind of potential with leaky boundary conditions, one-side leaky boundary conditions. So this is considered by Gamo's paper. But in quasinormal modes side, we consider a two-sided open boundary condition. One way, it's only falling into the black hole. Another way, it's escaping to infinity. So nothing comes from infinity and nothing comes from black hole classically. And you see that again, this about half-century rule applies. So this Vishveshvara, this is a pioneering paper about this quasinormal mode. Actually, he found first he found this ring down oscillations, but this is also again 40 or 50 years gap. So it should be advantageous for us to learn some lessons from this non-Hermitian physics. And the interesting thing is that this black hole gravitational waves are macroscopic, non-Hermitian classical system. That's a very interesting difference from many non-Hermitian systems in small microscopic and quantum systems, right? So it's very interesting realization. And the QNM frequency in this sense is its complex eigenvalue corresponds to poles of Green's functions, or in terms of this quantum mechanics, it's poles of ace matrix. So in black hole perturbation theory, we obtain the wave equation in the curved space-time, and with some source term, we first consider Green functions, and then to obtain the time domain waveform in terms of the spherical or spheroidal harmonic decompositions, then we need to integrate this Green function and source term. And also we need to perform inverse Laplace transformation with e to the minus I omega t. Then instead of calculating this contour along real axis, we can close this contour on the complex plane. So here in this talk, I often use this conjugate complex plane because imaginary part of the quasinormal frequency is always negative. So it's useful to use this conjugate complex plane. Then these are the QNM poles. So QNM frequencies are poles of the Green's functions. And we need to pick up the residues of all the poles, and also contribution from a branch cut, which I don't explain in more detail in this talk. But in the language of the nuclear physics, these modes, right-hand side modes correspond to resonance modes, and left modes correspond to anti-resonance modes in terms of nuclear physics. But we sometimes call that in the QNM context, so this is ordinary mode, and this is mirror mode or retrograde mode, or something like that. But in any case, important thing is that we need to pick up all the residues and obtain this kind of structure. So this tail comes from the contribution from branch cut. And the first term is precisely comes from this residue of all the QNM poles. And the important thing is that we can factorize these dependence into the initial data dependent term and the independent term. So this ILMN is an initial data dependent term involving this source term, and omega and b are independent from initial data. And omega is the QNM frequency corresponding to the pole of the green function. And b is the excitation factor. It directly comes from residue of the QNM pole. So omega and b are independent from initial data and depend on mass and angular momentum. So after normalization, it can be described by single parameter, so A over M. So it's very robust test of GR. And then there is a many interesting connection of the non-Hermitian features of black hole QNMs, complex eigenvalues, non-unitary evolution, modeling completeness, and non-orthogonality of spectral instabilities. So this is now recently very hot topic too. But today I will focus on this regularized norm and exceptional points and about crossing and resonant excitations. Yes, so I will explain this about crossing and resonances based on my recent work. Okay, so motivation is this anomaly found by Onozawa in almost 30 years ago. Okay, so Onozawa found this anomaly in car QNM spectrum. So this is car QNM spectrum. So this real part and conjugate imaginary part of the car QNM spectrum, starting from this fundamental mode, first overtone, second overtone, third, fourth, fifth overtones. And this diamond, open diamond, corresponds to non-rotating case. It's Schwarzschild QNMs. And as you increase the spin, then these frequencies going in this way, and eventually collapse into this so-called accumulation point or critical frequency at the extreme limit. However, almost all the modes will go here, but only fifth overtones turn around here and making some very, very interesting shape here, opposite shape, right? Very, very strange about this spin. Spin is almost 0.9. And Onozawa performed this numerical computation up to 20th overtones. However, he found only these fifth overtones behaves this in strange way. And many researchers, so after this Onozawa paper 30 years ago, so many researchers have tried to resolve this problem. However, so and all the calculations with more a sophisticated technique or more efficient computers, but all the calculations just reproduce Onozawa's result, but physical origin had been failed. So I was interested in this problem. Since this is big, difficult problem, so I tried to resolve this by following the golden rule of the physics. So this is a famous story of this foundation of the Newton's gravity. So first, Tycho Brahe accumulate very precise data set of the movement of the planets, and Kepler found empirical law, and Newton finally explained from theoretical framework. So I just follow this rule. So first, what I did first is just calculate this current QNM frequency and excitation factor very, very precisely. And it turned out that actually this was the first correct computation of the curve excitation factors. And then I found empirical curve, some beautiful curves in the trajectory of this omega and b in terms of spin, black hole spin. So they are hyperbola and Lemniscate of Bernoulli and quarter power Lorentzian function. And then I finally developed the non-Hermitian theory of quasinormal modes and analytically derive all of these curves. So first step is the computation of car excitation factors, and actually earlier works reported different values by different methods. So, and no agreement was made before my work. And I obtained I calculated excitation factors by using two methods and obtained the same value by these two independent methods. So one is this River, Norad, Mano-Suzuki, Takasugi method. And another one is the new formula for excitation factor by using this regularized norm or by orthogonal product norm developed in this paper. So I use these two methods and obtain the same values. And then after that, three groups, including me, too, calculated independently. So this group uses Sasaki Nakamura equations, and my group with Keiichiro Kubota, I calculated again using confluent Hoin functions. And then another group tackled this calculation by using this River, Norad, MST method, same method, but independent implementation. And all of the results are now agreed each other. So this establishes a nice base point of the black hole perturbation study. And I made this data set public in Zenode website. And now you can go to this website by using this QR code, and you can download the set of the data set. Now it's a QNM frequency and the separation constant and the renormalized angular momentum used in MST method was calculated in up to 40 digits. And excitation factor is mass imprecision. But this is, I covered various spins, spin 0 to almost near extremal regime, and covered up to the 7th overtone for gravitational and electromagnetic and scalar field perturbations. Okay, so after armed with such a precise data, then I tried to find out some empirical rule. Okay, so this is a Ka-2-2 mode in harmonic decomposition. And you can see this result is just reproducing the Onozawa's result exactly. And 5th overtone is turning around here and going into some unisolated point, which is unrelated to this accumulation point. So and everyone was thinking that this is some strange behavior of the 5th mode, but I noticed that. So 6th mode is slightly distorted when 5th one is turning around. So if you zoom in this region here like this, so not only 5th one, but also 6th one is distorted very, very slightly. So you may think that, okay, it's such a slight change, that maybe no problem. However, if we looked at this excitation factor, it's very interesting. So this 5th one and 6th one is amplified simultaneously. I mean, at the same spin value, they are amplified in a very peculiar way because all the other excitation factors following simple spirals, but they are against such a simple spiral and amplified in a characteristic way. Okay, 5th one is okay in a sense that because QNM frequency is already very strange. So you may not be surprised that the behavior of the 5th excitation factor is strange. However, this 6th one is also strange. But even if that this 6th frequency is very slightly changing, but this change in the excitation factor is very significant. So from this plot, I have some lessons. Maybe this phenomenon involves two modes rather than single mode, and the underlying connection between omega distortion and beam amplification should exist. So this should be some underlying physics. And in this sense, I like to call this mechanism as black hole dissonance. Dissonance is some opposite of the consonance. It's a harmony created by simple frequency ratios in music, right? So this is a very close frequency and amplified amplitude. And this is a typical pattern of the actually dissonance in music. So this is a representative dissonance in musical piece. So this is minor second. So it's very close frequency, and it's typically appeared unexpectedly, breaking some regular patterns and intentionally a loud sound. But it's not just a noisy sound, but this kind of dissonance should be introduced on purpose by composers to create some very attractive music. Right? So it's in that sense, this dissonance is important in music. And now we will see that dissonance is also important in gravity. Okay, so I continued the calculation of the QNM frequency and the excitation factors for higher multiple. So this is 3-1 mode. And we found very complicated structure here. And then if we zoom in, yeah, this kind of structure. So very interesting. So we see that in this case, we can see that the successive avoided crossing. So I would call this as avoided crossing, and I will explain this later. But they are avoid to be crossing each other, right? So first, maybe we can see this clearest example between fifth overtone and the sixth overtone. So this is approaching each other, almost colliding, but avoid each other and repulsive, right? So this blue and the purple one. So this is called avoided crossing. So I will mention it later. But during this avoided crossing, this B excitation factor is amplified with this figure 8 pattern, right? And before such a clearest avoided crossing between fifth and sixth overtones, this fourth overtone and fifth overtone also exhibit mild avoided crossing in this way, this fourth one, fifth one in this way. And after that, fifth one and the seventh one, sixth one, the seventh one also create some loose avoided crossing. And correspondingly, we see that very small mild amplification occurs, but very peculiar pattern, right? And we note that this avoided crossing can be well described by the hyperbolic curve, and these excitation factors can be described by this lemniscate of Bernoulli. And if we write down those curves in polar coordinate, they are just inversely related. So very, very interesting and tantalizing hint. Right, and then also we can also check this resonance peak. So this is a difference between excitation factors and also inverse of the difference of the QNM frequencies. So they are almost overlapping after rescaling of the proportional constant. And I also plotted here the quarter power Lorentzian as a black dotted line, and it's almost overlapping here. So this is a clearest, sharpest avoided crossing between fifth and sixth overtone in 3-1 modes. For mild overtones, mild avoided crossings, we can roughly see that they are following this rule. So they are almost inversely proportional to each other, and the peak can be described by this quarter power Lorentzian peak. And this is 2-2 modes. So fifth and sixth modes also roughly follow this rule. So from this, we can see that this is sharp avoided crossings lead to prototypical form of this phenomena, and mild crossings result in the distorted patterns, just distortion of prototypical patterns. And one may think that, okay, this comes from maybe complicated structure of the Chokorosky equations. However, interesting thing is that so this structure also shows up in a very simple setup like this. So forget now about the black hole perturbation theory or effective potential and just consider this two rectangular, so double rectangular barrier. And just using this potential and using this differential equation, second order differential equation with eigenvalue problem, then if I solve that, we obtain again this kind of structure. So I omitted third figure about the resonance peak figure, but that's the same, also the same. So you can find, if you are interested in, you can find this plot in my appendix of my paper. So this is so-called free and elephant type model. And this is used in the context that, for example, this is residual potential and some small bump originating from the matter distribution around the black hole. So this is a very simple model of such a kind of model in the context of black hole physics. But in any case, so this, even in this simple toy model, we can see the same structure of our crossing of QNM frequency and the excitation factor amplification follows just lemniscate of Bernoulli. So this black dashed curve, almost overlapping green and red, are the lemniscate of Bernoulli. And this is the hyperbola. So this black dashed curve is hyperbola. And if we change the parameter very slightly from 4.3 to 4.31, then this is mode reconnection, mode switching happens, but still avoids each other and still amplified in a figure 8 shape. So these are very beautiful empirical curves. Very beautiful. Too beautiful to be a coincidence. So there must be some physics behind it. And then, continuing the research, I found that should be the universal resonance phenomena for generic QNMs. And what I did is analyzed this system as a pair of isolated QNMs as a non-Hermitian two-level system and derived these curves analytically. And then maybe I can now explain the abolic crossing, what abolic crossing is. Actually, this is well known in the quantum mechanics field, bound state, even it's written in the Randall Lifshitz textbooks of quantum mechanics. And famous example includes the band gap at the edge of brilliant zone. So this is also classical textbooks of the solid state physics by Kittel. And this energy gap is also related to this abolic crossing. So when the two eigenvalues are approaching, they will avoid each other. And more clear example is this Stark effect. So mild abolic crossing made in Stark effect. So this effect, so if you increase the amplitude of the electric field, so this degenerate energy will split each other and going in this way, so almost colliding but avoid each other. The same thing also happened for Zeeman effect too. So it's very well known, and Randall Lifshitz textbooks, these abolic crossing features are derived in this way. So if you introduce the perturbation of delta V of the potential, and if the two eigenenergies are close, then you cannot rely on the standard linear perturbation theory of time-independent perturbations, and you need to diagonalize this Hamiltonian. And after diagonalizing this Hamiltonian, energy eigenvalues is given by this equation. So suppose that if they are crossing, not abolic crossing, but if they cross each other, then this E plus and E minus should be the same, which means that you need to satisfy two conditions. So this squared and this squared should be vanishing simultaneously. So these two conditions. However, if you have one parameters, so single parameters, then you cannot satisfy two conditions in general. So that's why this abolic crossing happens. And you can derive a hyperbolic curve from these equations. So this is abolic crossing in quantum mechanics. And actually, in astrophysics, we see abolic crossing too. This is happening for stellar oscillations of ordinary stars or proton-neutron stars, and also occurs in neutron oscillations in matter known as MSW effect. And that was the key to resolve the solar neutrino problem. So the abolic crossing is ubiquitous in this sense. And then a abolic crossing in non-Hermitian system. So this is a paper about such a case. And in this case, instead of real energy eigenvalue, we have complex energy eigenvalue, and now it's complex plane. So this real part and imaginary part. And in this case, this mode switching happens. So case one is these top panels. Okay, real part is repulsive and imaginary part is a crossing. So from A to, so one energy eigenvalues starts from A and then end up with B. Another one comes from A prime and to go A, B prime. So real part is repulsive, but imaginary part is crossing. But if you change the parameter of the system slightly, then you would obtain another trajectory starting from A to B prime, A prime to B. In such a case, imaginary part is repulsive and real part is crossing. So this is abolic crossing in complex eigenvalue plane. And this point here, this crossing point is called an exceptional point. And this exceptional point, or EP, was introduced by this Toshio Kato's seminar textbooks in 1966. And now it's very important feature in non-Hermitian physics. It's branching point where both eigenvalues and eigenvectors are coalesce. And we cannot be then diagonalized matrix, and we left with Jordan blocks. And this is a unique feature in non-Hermitian systems. You can see this review paper by Asida Gon Ueda. And this is EP. This is some schematic picture of the structure of the EP. And the EP is also very interesting from the experiments. Many experiments in optics, photonics, and condensed matter, or solid-state physics. And for example, this resonance enhancement or unidirectional transport, a very high sensitivity due to the unique time dependence here. So, and I will mention this later in the context of black hole QNM too. But many interesting things was discovered in a wide range of the physics disciplines. Okay. And we can derive such as structure by using this non-Hermitian theory of QNMs. So starting from these Chukovsky equations, but this is not like a wave equation, but this is non-Hermitian system. So we have this diverging behavior at infinity. So it's not L2 norm does not work. So we need to introduce a regularized norm. So inspired by this numerical nuclear physics and this non-Hermitian physics textbooks, I introduced. So I generalized such a definition and introduced this bi-orthogonal product for Chukovsky equations. And this is the usual part corresponding to the usual part, and this is the boundary part. So you can subtract the boundary part to make this product be finite. And from this equation, you can easily show that this is orthogonal. And this is corresponding to the left eigenvector or right eigenvector in terms of, in the language of non-Hermitian physics. And sending this omega k to omega n formally, I obtain this norm squared. So this is a definition of norm squared based on this bi-orthogonal product. And after obtaining such expression, and I just still, I keep this C to be general. So if this C is a real axis, so it's a standard torus coordinate. If you integrate this to be on the real axis, then this expression reduces to the so-called Zeldovich regularization used in nuclear physics. And if you keep this to be complex contour, then we can utilize this complex scaling method used in the nuclear physics too. And in this sense, you can modify the contour from just a real axis to complex plane as you desired to make this behavior converging. In such a case, you do not need the surface term because surface term is vanishing in such a limit. So that's a very useful contour. And then after defining such a norm squared, we can derive analytically a new formula for excitation factors. So now excitation factor is inversely proportional to norm squared. And I also calculate this factor numerically by using complex scaling method. And I confirmed that this combination also from the numerical calculation. So it matches the excitation factor obtained by Rebar's NORAD MST method. Yes, and then with this norm squared, we can show this empirical curves. So this avoid crossing and complex plane, then we can obtain this kind of structure. So it's similar to what we saw in the previous slide. And we can derive this hyperbola and Lorentzian to the 1/4. And then after that, using this formula and the fact that this A is almost vanishing near EP, then you can find this Lemniscate curve from this equation. And this establishes that this phenomena as a universal effect for black hole QNM at near the EP. So short summary of this part is that we found these QNM frequencies follows hyperbola and excitation factors amplified following Lemniscate of Bernoulli, and resonance peak follows quarter power Lorentzian. So these are universal resonance effect at avoid crossing near EP. And this resolves the physical origin of the 30 years anomaly in QNM spectrum. And this was the first identification of EP in gravity. And this resonance can be used as a novel tool for black hole spectroscopy and diagnostics. In this paper, I mainly focus on the high-spin car QNMs. And recently, in the ongoing work with Keiichiro Kubota, we found this abort crossing also occurs at the low-spin car QNMs, so almost zero. So, and this is very interesting. So this is abort crossing of QNMs and resonant excitation of the excitation factors, and also this pole skipping occurs. Pole skipping between QNM pole and Matsubara zero modes. So here, this phenomena resolve some mystery about these QNMs near algebraically special mode. And hopefully we can put this paper on archive soon. Okay, so let me briefly introduce some further progress of the EPs in gravity. So after now a discovery of EP in gravity, now there are many papers about this. So in the context of rotating black holes or non-rotating black holes with some perturbations or coupled systems or nonlinear effects. So I can just briefly introduce some of them. So this paper, in Yang et al. Paper, they pointed out that this resonance effect should be accompanied by this time dependence. So this linear time dependence multiplied by this e to the I omega t, that's a standard time dependence. So in this case, similar to the double rectangular barrier potential I discussed in the previous slides, they consider this residual potential plus some small bump. So this is a model of the black holes surrounded by matters. And they found that this kind of expression is important to extract the structure of the resonance. And recently we derived this form from the first principle calculation of the green functions. So assuming double pole, existence of a double pole in the green functions, and evaluating the residue of the second order poles, we directly obtain this form. Right. Then this is a better basis of the description of the ring-down phase oscillations, and also this we performed that and fitting and clarifies that this model provides accurate fitting compared to the standard QNM fitting. And then those two papers, we assume the a priori knowledge of the resonance, location of the resonance, right? Because we assume that the t to the e to the t times e to the I minus I omega t. But if we would like to use this resonance structure to detect new physics, then in that case, in general, we do not know the location of the resonance in the parameter space. So it would be good if we can look for the agnostic resonance extraction. So that's why we perform such a calculation in these papers. So using these techniques of the QNM fitting, we tried, but I don't explain this plot in more detail, but the conclusion is that it's still challenging. So naive way of fitting is still challenging for the agnostic extraction, but more sophisticated approach exists. And now we are considering such a way of orthonormalized QNMs or machine learning technique for the autoencoders. So these may be helpful to extract resonance in a more efficient way. And we also considered resonance in a coupled systems. So I mentioned that the resonance may be useful to probe the new physics. So in that direction, we consider Einstein-Maxwell axion system and formulated the excitation factor for general coupled system and found a similar resonance structure like this. So this result strengthens the potential to probe new physics. And this is another interesting paper by Cavalcanti and collaborators, a series of papers, and they found this abort crossing and path-dependent evolution in massive scalar field, QNMs. So this is the model switching I discussed previously, and also happening here too. And this is a branching structure near the exceptional point. So the physics is depending on the path of these Riemann seeds. Right. Okay, so let me summarize my talk. So it's very interesting. So this is what I call non-Hermitian gravitational physics is just beginning, and a growing landscape of novel phenomena is emerging, such as void crossings and resonant excitations. And cross-disciplinary ideas from, for example, quantum mechanics or nuclear physics or condensed matter physics will derive the next discoveries. So very, very exciting regime. Okay, so let me stop here. Thank you very much.
Thank you for the really nice talk. Are there any questions?
Can I ask a question?
Yeah.
Sure.
It's a basic one. I'm actually quite confused what you mean by hermicity. So for example, in quantum mechanics, hermicity actually often comes from the boundary conditions of the continuous operators. So for example, the examples you gave, for example, Cattell, right? I'm sure he's talking about Hamiltonians that are in fact Hermitian. Or even WKB tunneling. I don't think you're assuming the underlying Hamiltonians is not Hermitian, right? It's just that when you have a barrier, there's tunneling. So I'm a little confused. Like what exactly is Hermitian?
Yeah.
And what exactly is not Hermitian?
Yeah.
I'm confused about that.
Yes, thank you. So that's the notion of the hermicity is not only the potential or Hamiltonian, but also due to this boundary condition. So even if your Hamiltonian is looks like Hermitian or standard Hamiltonian, if you impose this leaky boundary condition, then system is non-Hermitian. So
can you say that again? What conditions? If I impose what?
Yeah, I'm not sure if I wrote down the condition here, but it's a boundary condition. It's something like yeah. Let me see if I found.
Okay.
If I no, maybe I don't find, but it's yeah standard yeah boundary conditions. So this Hamiltonian and yeah, you see this wave function, the Hamiltonian the wave function, and they integral, and then they should be equal to the Hamiltonian dagger of the such a combination. But this equality holds or includes the notion of the boundary condition here. So in the usual Hermitian quantum mechanics, the boundary condition that the wave function should vanish its infinity is implicitly assumed. So if you remove such assumption and replace the boundary condition to this kind of leaky boundary condition, then you cannot satisfy this condition of the emissivity. And yes, the system
leaky. I think your word is leaky. Is that right? L-E-A-K-Y?
Yeah, leaky, yes.
Outgoing. In what sense? Your ET minus KR, you mean because some of them are complex? Is that what you mean? Your E and...
No, it's leaking from this potential well.
Oh.
Yeah. If this is infinite potential well, then it's bounded, right?
Right.
But it's now escaping from this regime, and this is leaking from this well and escaping to the infinity. Yes, that's outgoing boundary condition.
I thought that's what you said earlier, though. I mean, as long as out to infinity, sorry, this is a basic question, but I thought out if you go to infinity, and as long as the wave functions do decay, then I thought it's okay, or at least a plane wave, right? Plane wave is not square normalizable, but delta function normalizable. And I think at least within physics, we still consider that as Hermitian, right? So I'm still not so clear that you are saying that even just toy model for nuclear decay, we would say the Hamiltonian is in fact non-Hermitian. Is that
Yeah. Even for this kind of simplest example, like box potential, for example, box potential. If you impose, maybe box or not well, just potential well, for example, here, right? Or the quantum mechanics textbooks. In that case, so if the boundary condition is just vanishing in the infinity, then you would obtain bound state. But if you do not have such a boundary condition, and instead you have outgoing and ingoing boundary conditions, then you would obtain complex eigenenergy, and it is the non-Hermitian system. Maybe, if I have some figures or equations, I can explain more, but that is included in my, I think, different slides. So now I don't have that, but maybe later, if we finish
I've
it.
always thought that when we talk about at least the quantum mechanics side, I've always thought that when we do that, we always assume that underlying physics is always unitary, right? And so if we at the fundamental level, because if we break it, then we would actually be saying that time evolution is not unitary. Right, which kind of I think is a big deal. No, if we say that time evolution is not unitary, I think that would be a big deal. No, so
But there are several a point of view. So first one is just you So first attitude is just you consider some special space. I mean, some restricted space. It can be ideally is unitary, but now real life is not unitary. That's one way to consider, and another way is just a consider such a so everything is unitary, but you can consider some opposite way. So you can consider this kind of system, and it's not unitary. And the third point of view is just experimentally you consider such a system. And yeah, there are many kind of attitudes, but yeah, interesting thing is that it corresponds to actually this condition for boundary condition for QNMs. This QNM can be obtained by imposing these conditions. So this is escaping to infinity and falling into black holes. If you impose these two boundary conditions, then in general, you cannot satisfy such a boundary condition for arbitrary omega. And these two boundary conditions discretize this omega into the discrete complex values, and that is a QNM frequencies. So that is related to each other. Yeah.
Okay, thank you. Thank you.
Yeah, thank you.
Okay, are there other questions? Geo, I guess you have one.
Yeah, thank you very much, Motohashi-san. Very nice talk. So I have a question about this double rectangle potential case. Can you go to that slide?
Yeah. Okay, this one. All right.
Yeah.
Yeah.
So in a usual Kerr overtone case, when those trajectory in the frequency domains are labeled by spin, but in this case, what labels these trajectories?
Yes, this is in this case I vary this B parameter, so distance between the primary box and secondary box. So keeping this D and V0 and V1 are fixed parameters. So if you increase B, then this is going like in this way.
Okay, so it's the size of the perturbations.
Yeah, size. No, size, not the location of the perturbations. Yes.
Right.
Yeah. Right. But even if you fix B and, for example, increase V1, then a trajectory is different. The total shape is different, but qualitatively, this kind of structure occurs. So when they approach each other, they are repulsive each other. Yes.
Okay.
Mm.
And so this kind of system is associated with the pseudo-spectrum instability, right? And do you have any comments about the relation between this avoid crossing and also the spectrum instability?
Yeah, that's the good point. And yes, this is precisely occurs due to the QNM instability. So QNM instability means that if you introduce this small perturbation, even if the perturbation is very small, and if they are far away from primary peak, then QNM spectrum is completely different. But in general, recent studies suggest that even if a spectrum is completely different, then still time domain ring down signal is similar, right?
Yeah.
But in that sense, mostly that the lesson applies to this avoid crossing case. But the interesting different point for this avoid crossing things is that we have different time dependence caused by this t to the t times e to the minus I omega t. So that's the little bit different peculiar behavior to the this model. Yes, that's not happening for general QNM instability case. It's due to the closeness of the location of the two poles. So my short answer is that this QNM instability is just a movement. So small perturbation moves the QNM spectrum completely, changes completely. And then along that case, that migrations, if two QNMs approach each other, then it generally repulses each other. and there exists some characteristic features in time domain.
Okay, so
Yeah.
they are not necessarily related in some sense.
Yeah, or not necessarily, or
Okay.
included, or yes. Yeah, QNM instability. This
Yeah.
is caused by QNM instability too, but in the car case, it's not QNM instability, just
Right. Yeah.
changing the spin parameters. So it's also happening in non-QNM instability system too.
Sure. Sure.
Mm.
Thank you.
Yeah, thank you.
Okay, are there other questions? It seems right now not.
Maybe I can also ask one more if
Please, Chair, go ahead.
Yeah, go ahead. Yeah.
Yeah, maybe it's about your ongoing work. I don't know how much you can disclose, but I mean it's about like so in the case where you consider very slow spin, does that mean that you have to go to very high order overtones in order to see this?
Yeah. In this case, it's very high. This is
Okay.
eighth overtone, actually. It's
Ah.
eighth overtones, and this is very close to the imaginary axis. So it's frequency is very small. So yeah, I'm not sure if this can be observed in on ring down signal, but there is some a inconsistent interpretation about this QNM frequencies near algebraically special point, and this kind of structure resolves some of them. So previously, this modes was believed to be disappear or split away without any reason. But now we clarify that, okay, this is actually avoid crossing come between the standard QNMs and another one coming from the unconventional Riemann seed. This is a different Riemann seed beyond the branch cut. Then it creates avoid crossing here and then moving into the standard Riemann seed. So it's very interesting and so from mainly theoretical, but it's very interesting.
Yeah, sure. Thank you.
Thank you.
Got it.
Okay, then let me ask one more time. Are there some more questions? If not, thank you very much again for your nice talk.
Okay, thank you very much.